Okay, right to the point. At the center of the atom, it's called its nucleus, and is made up of neutrons that have no charge and protons that are positively charged. It's the number of protons in the nucleus that give the atom the identity, a personality so to speak, called the element. The number of such protons in each element is called the atomic number. One proton is hydrogen, two protons is helium, three is lithium, four is beryllium, five is boron, and so on. If you change the atomic number, you change the element. Gold has 79 protons, its atomic number is therefore 79. Remove one proton, and you have platinum. Add one, and you'll have mercury. Neutrons don't mostly change the properties of an atom and don't change what element an atom is. Five protons will remain boron, regardless if there are four, five, or six neutrons. It'll simply remain boron. However, they do have two important parts to play. Being almost the same mass of a proton, they change the mass of the atom overall, called the relative atomic mass. Hydrogen with one proton also has one neutron, making it twice as heavy than if it were just a proton on its own. While the number of protons will always stay the same for a given element, the number of neutrons can alter. For example, oxygen with 8 protons can have 8, 9, or 10 neutrons and still remain stable. These different masses of the same element are called isotopes. Now we all know that like charges repel each other. So the second part that neutrons play is to serve as a sort of buffer between the positively charged protons. However, the neutrons certainly don't glue the nucleus together, and its buffering effect is not nearly sufficient alone to stop the positive protons repelling apart. So what is it that holds it together? Well, by the strongest of the four forces of physics, of course, that of the aptly named strong nuclear force. It is so strong, in fact, that it's around 1,000 times stronger than gravity, but it only works at extremely short distances, too short to fathom. Now, should the atom remain consisting only of protons and neutrons, then we have a fundamental problem. Everything would be positively charged. Atoms could not form molecules, and you and I would just not exist. To solve this problem, in steps the electron, a tiny particle some 1,800 times less the mass of a proton or neutron, but has an equal and opposite charge to the proton. Now, each proton in an atom is matched with an electron, hence there is no overall charge, and the atom is neutral. But this is not always the case. Atoms can gain or lose electrons, giving them a small positive or negative charge, and this is a fundamental of chemistry. More about that in other videos. But how are the electrons positioned in respect to the nucleus? Well, it was initially proposed by the British physicist Joseph Thomson that the atom had no nucleus at all, but rather a ball of positive charge, now known as protons, with electrons spread evenly through it like currents in a plum pudding. In fact, we call it the plum pudding model. But then came along a New Zealand physicist called Ernest Rutherford, who wanted to prove Thomson's plum pudding model via his so-called gold foil experiment. Ironically, the experimental measurements showed that this model was completely wrong, and in fact dictated that the atom is largely empty space, with the nucleus consisting of more than 99.9% of the atom's mass concentrated in a tiny volume at the center with electrons circling around it. In fact, most of the volume of the atom is made up of the orbiting electrons, some 100,000 times the diameter of the nucleus. This could be related to putting a marble in the middle of a football field. But what were these electrons doing? Enter Danish physicist Niels Bohr, who from studying Rutherford's measurements predicted the most likely positions of the electrons and postulated that they followed specific orbits of specific energy around the nucleus, akin to how the planets orbit the sun. In fact, it was named the planetary model. But alas, although his model worked well for the simplest atom, hydrogen, and explained how such atoms emit light, it did not do so well for larger atoms, and the theory was flawed. To the rescue came a German theoretical physicist, Werner Heisenberg, who changed it all with quantum mechanics that stipulated that one can't in fact know with certainty both the momentum and position of an electron, or any particle for that matter, and so cannot position the electrons in neat circular orbits. He further stipulated that electrons can't be thought of as particles, but rather as a blend of both waves and particles. This quantum theory said that the positions of the electrons around the nucleus could only be described in terms of probability, that being regions in which the electron is most likely to be found, giving rise to fuzzy clouds around the nucleus. The denser the cloud, the greater the probability of finding an electron occupying that locality. Hence his model became known as the cloud model. Heisenberg's model also served to answer a question that had bothered physicists for years. Although the opposite attractive forces between the electrons and protons explained why electrons do not fly off from the atom, it did not explain why the electrons do not collapse into the nucleus via their attractive force. Rutherford tried to explain this in his model by asserting that electrons were held in orbit by their velocity around the nucleus, being the same reason why planets are held in orbit around the Sun rather than colliding into it under gravity. However, unlike planets, an electron is electrically charged and loses energy via emitting electromagnetic radiation as it undergoes changes in velocity and direction. This is a problem because this loss in energy results in the electron slowing down and death diving into the nucleus, and the atom will collapse. Heisenberg's model solved this dilemma. Although it's out of the scope of this lesson, a somewhat oversimplified explanation can be given as this. We can assert that the negatively charged electron cloud will want to draw nearer to the positive nucleus. But as it does so, the cloud will condense, resulting in the negative charges getting closer and closer. And as they do, they will repel each other and move outward into a less dense environment until a happy medium is achieved between the electron cloud density and its attraction to the positive nucleus. This happy medium of electron cloud placement is its orbital. Lastly, in chemistry, it's important to note that the magic all happens at the outer electron boundaries of the atom. And this makes sense as it's these outer electron boundaries that will meet between atoms and interact. These outer electrons are called valence electrons and are fundamental in understanding chemical reactions